Hi, my name is Lucas, and in this summer I created a program which allowed us to observe the interactions of helium-3 test particles with ion cyclotron waves. Now, our motivation behind making this program was that under normal conditions, the ratio of helium-3 to helium-4 is around 1 to 10,000. However, it's been observed in certain solar energetic particle events, or SEP events, that the ratio of helium-3 to helium-4 can be enhanced to around 1 to 1. And this dramatic enhancement is of interest to us because and it's believed that a possible cause of this enhancement is that helium-3 can preferentially resonate with what are known as ion cyclotron waves. And by creating our program, we're able to view the interactions of helium-3 and ion cyclotron waves to notice if this preferential resonance is actually occurring. It's not letting me move. Okay. And on this slide, you can see an example of one of these measurements of the enhancement of helium-3 to helium-4, whereas in these box regions, you can see an increase in helium-3, but no increase in helium-4. And that's actually interesting because that shows that in some of these solar energetic particle events, not every ion type is energized equally, and it can in fact be where only helium-3 is ionized or accelerated, not helium-4. Now, to understand why this might occur, we need to go over some plasma basics. Now, the plasmas we are looking at are low density collisionless plasmas, and they typically exist within a background magnetic field. Ions in these plasmas will move parallel to the magnetic field lines in what are known as Larmor orbits, where they will move in a helical motion following the path of the magnetic field lines. These have a characteristic radius known as the cyclotron radius, which is the mass of the ion times its perpendicular velocity over the charge of the ion, times the strength of the magnetic field, and they have a characteristic frequency known as the cyclotron frequency, which is the charge of the ion times the strength of the magnetic field over the mass of the ion. Now, these Larmor orbits can generate what are known as ion cyclotron waves. These waves have a dispersion relationship, which is as follows, and I'm not going to go into detail on it, but what it is important to note is that the frequency of these ion cyclotron waves can have a frequency close to the ion or to the cyclotron frequency of the ions. This means that these waves can interact efficiently with the ions. One such interaction that we're interested in is known as a resonance interaction. This interaction occurs mainly when this following condition is met, where the parallel velocity of the ions is equal to the frequency of the wave minus the cyclotron frequency of the ions over the parallel wave number of the wave. And when this occurs, the ions are expected to gain energy quickly, and you would see their Larmor radius increase in a spiral motion, as can be seen by this animation. And what's interesting to note here is due to helium-3's unique charge to mass ratio, it is believed that certain ion cyclotron waves will preferentially resonate only with helium-3 while not resonating very strongly with helium-4. Now, in order to investigate this, I created a GPU-based program in the Julia programming language, which allows us to quickly observe the interactions of ion cyclotron waves with helium-3 and other ions. What's advantageous about my program is that it has very fast runs when compared to more complicated programs. So 10 minutes compared to 4+ hours for a more complicated self-consistent program. It also allows us to ignore more complicated effects that arise in self-consistent simulations, such as collisions between the plasmas or other waves that we're not interested in, which allows us to explore solely the interaction of ion cyclotron waves on the system and not some unrelated waves. So one example of data from our program, and the details of this are not important. However, it's 16 million electrons interacting with what are known as visceral waves. And what this shows is that by being able to view the positions of each particle individually, we can actually see certain structures arise that might be hard to notice when you're just looking at bulk average data. For instance, in this case, you can see spiral patterns forming as the electrons move. And it's also important that we can look at other waves than just ion cyclotron waves, because in the future, we might be able to add whistler waves to our system as a source of noise to see if certain structures that we arise when we're using solely ion cyclotron waves are actually stable and actually arise when there's noise involved. Another example of output from our simulation, and this is a run where we had an ion cyclotron wave that we expected to preferentially resonate with helium-3. However, helium-3 being the blue line, helium-4 being the green line, from just bulk data, it's difficult to notice a difference in the behavior of helium-3 and helium-4. However, when we view data in a more complicated way, in this case, a density plot of the ions in velocity space, we can notice how helium-3 on the right is a much more orderly structure, and apologies for the contrast, it's actually kind of difficult to notice it. Whereas helium-4 on the left has a much more chaotic structure, which implies that helium-3 actually is resonating with the wave, whereas helium-4 is not. Another run in our most recent runs have been looking at waves that we expect to resonate preferentially with helium-4. However, we notice in strong magnetic fields, all the ions actually tend to accelerate to the resonant velocity, where they will then maintain equilibrium. This is interesting because we actually expect that at this resonant velocity, the ions would begin to heat rapidly. However, we don't notice that. We notice heating up until they reach the resonant velocity, whereas they then maintain a stable temperature. Another interesting thing about this run is, while it's difficult to see a difference between, for instance, helium-3 in the blue and the behavior of hydrogen in yellow, what you can actually notice is when you look at their positions over time, hydrogen tends to form a single clump that will move with this resonant velocity in a helical pattern, whereas helium tends to form 3 separate clumps. We believe this is due to the helium going into different harmonics with the wave. But we need to investigate this further to actually find out if that is in fact the case. So in conclusion, now that the infrastructure of this program is in place, we will be able to do many more runs very quickly to explore the complex interactions of helium-3 with ion cyclotron waves. We can also in the future do an implementation of this program on Perlmutter supercomputer, which is a supercomputer being created by NERSC that, when it is complete, will be the 4th fastest computer in the world. And this computer will allow us to do either very large runs with on the order of like 1 billion particles, or what's more interesting to me at least, is that we can do many runs at once. And so we could explore a ton of the initial conditions to see how they actually relate to the evolution of the system. After that, we will attempt to reproduce the results from our simulations using more complicated techniques like PIC simulations, which can allow us to see if the results from our simulations actually hold up under more complicated systems. Thank you all for listening, and thank you to the NSF for funding our research.